one more example here that I'm going to do for you. I've got the function y equals x squared, I've got the function y equals x plus 2, and I want to rotate the area that's enclosed by those two around the x-axis. So I'm going to go ahead and graph these two. Y equals x squared, yeah, looks like this. Okay. Y equals x plus 2 is 1, 2, okay. Slope of 1, looks something like this. And really, all I'm interested in is the area that's bounded by those. I'm going to rotate around the x-axis. So I'm going to get rid of this extra stuff just because it's unnecessary and cause extra lines to be written around, etc. So I'm going to rotate that around the x-axis. That means I'm going to have something that looks kind of cylindrical or symmetrical to that, roughly like that, butterfly wings or something. I don't know what it is. Anyway, so what do we need here? Well, if we're going to rotate that around and we want to know, we want to get that volume, okay, well, what do we have? We have, we can cut a slice like this. That'll give us a cylindrical shell case to do. We could cut a slice like this. That would give us a washer, right? Now, the way I decide which one of these I really want to do is that I'm going to look at a function like this and I'm going to say, well, since y is x squared and y is x plus 2, they're already both solved in terms of x. I'd really rather do dx if I have the choice. I have a choice here, right? So I would rather do dx. And so as a result, I'm going to slice it this way. Say, okay. That's the first thing I want to establish is, am I doing dx, am I doing dy? Once I establish that I'm doing dx, I say, well, that is perpendicular to the axis of rotation. Perpendicular to the axis of rotation means when I cut that thing out, I got this. That means I've got to find the small r, I've got to find the big R, and I'm going to have pi r squared minus pi r squared, or one's pi big R squared minus pi little r squared. So I need to do that. Little r, that's the distance from here up to the curve. And I notice that is the curve. Everywhere I look, that is the curve. It's from here up to the curve. It's from here up to the curve. It's always the parabola. So that distance right there, which is a y different distance, is this y distance. That's little r. Little r is x squared. Big R, well, big R is the distance from here up to the line, right? Wherever it is that I may be, I'm going up to the line. Big R is x plus 2. So pi big R squared, x plus 2 quantity squared gives me x squared plus 4x plus 4 minus pi x squared. And that x squared is squared, so it comes next to the 4. And all of that is dx, and so far everything is well and good. The one thing that I haven't dealt with yet is limits of integration. Well, again, this drives where I'm looking for those limits. I'm looking for x values. I'm looking for all the x values between here and here. Well, what would those x values be? Well, this one down here and this one here and here, those are where those things intersect. So in order to find the limits of integration, I say, well, these are where x squared is equal to x plus 2, or y1 equals y2, whatever you want to say. And x squared minus x minus 2 equals 0. I factor that. And that tells me x equals minus 1 and 2. If that's minus 1, that's 2. My limits are minus 1 and 2. Once again, these integrals do not tend to be particularly complicated integrals. They tend to be raised to the power by 1 and divide by it. I've got my pi, x cubed over 3, 4x squared over 2, 4x, minus x to the 5th over 5. All of that evaluated at 2 and at minus 1. I've got pi, and what do I have here? Plug in the 2, I've got 8 over 3 plus 8 plus another 8 minus 32 over 5. And all of that minus, plug in negative 1, I've got minus 1/3. Plug in negative 1 1 here, I get plus 8. And plug in negative 1 here, I get minus 4. Plug in negative 1 here, I get plus 1 over 5. So what happens with that? I've got a pi outside everything. I'm going to go ahead and say I've got, I can distribute this minus sign, right? And that becomes a minus, that becomes a plus, and that becomes a minus. I can combine a few like terms here to clean things up. 8 and 8, minus 8, 16, that sounds like 8. Oh, 8 plus 8 is 16, plus 4 is 20, minus 8 is 12. That's all the constant terms. I've got 8 thirds plus 1 third. Sounds like 9 thirds, also known as 3. I've got minus 32 fifths, minus 1 fifth, minus 33 over 5. So that's 15, if I want that over 5, 75 over 5, minus 33 over 5, and that sounds like 42 pi over 5 would be the volume of that. So the point to take out of this is you aren't forced to either use the shell method or the disk method. You choose which one makes the most sense for you in that moment in time. And in some cases, you can't use one. If I was to try to use the shell method here, up here I'd be okay. But down here, I run into a problem just like I did before, because down in this region, the x on this side and the x on this side are both described by the same function. It's this function. Now it's symmetrical there, so I can get around it, but the fact of the matter is it causes me more headaches than doing the cut that is perpendicular to the axis of rotation. In this case, that makes the disk method easier.